Today I have my youngest son with me after a big absence.
Yep.
Why'd you come? Who invited you?
You did.
I
I was minding my business. All of a
must be
sudden, I got roped into this.
must be my Alzheimer's. Anyways, we have a great day today. We're going to be talking about. We're going to try to discover the center of the universe. Is there a center to the universe
Not
or
the
not?
galaxy, the universe, right? Not this.
Yeah, no. That's Andromeda, my girlfriend.
This is
But
the one.
no, question is, does the universe have a center? I mean, that guy has a center, but question is whether the universe does. Anyways, let's get to it. Hold your questions until the end. I sometimes forget to remind people, but at the end we will have open the floor for questions, and you are welcome to ask any type of question specifically related to the subject matter today, but otherwise no problem. Just ask any question whatsoever. No problem. Okay, so let's start here. And before I get to the end of the universe, which is the main course today, I'm going to be talking a little bit first about what I talked about these last 3 weeks, which is essentially about time. This word time that has entered the world of physics. And what I can tell you about that is the following. In physics, in science, we do not have any use whatsoever for time. Let me repeat that because people say maybe I misspoke. Time has nothing at all to do with physics or with science, okay? And you say, hold it, we've got GPS out there and tells us, what time it is, where we're at, all that kind of stuff. Yeah, none of that has to do with science. Science is about explaining a mechanism, especially in physics. You have to explain, how this universe works. And time is only concept
What
that
do you mean
is
by
used.
time, though? Because
We're going to go over that.
we do need a sequence of events to explain things. This happens and
Yeah.
that happens and that happens. Why did
Yeah, but
what follows what?
And
a sequence of events could be
well, that's for
sense of time.
description. That's
but
for
what I mean is
you're
that's-
describing,
yeah,
you're
but-
presenting. But science, where science
even when you're
vibrates,
explaining-
hold it. But science, where science vibrates, is in the explanation segment, which is theory. The assumptions include descriptions. For example, what we call the assumptions, the first few frames of the initial frames of the film. And there you can say, look, this is the sequence of events that led for this car that crashed against that one. And now we're going to explain what caused that.
But when you're talking about time, you're not talking about just a sequence of events. You're talking about using time as a concept, as part of the
per se.
explanation.
Right. And the issue here is that time has no purpose within the explanation, within a mechanism. Okay, the mechanism is objective. How did the window break? A stone went through the wall, through the window, through the frame. I don't need to talk about time in any sense. I don't have to say it took so much time, so much force, so much energy, so much mass. I don't need any of those concepts to explain why the window broke. We're talking about, just the physics part. What was the mechanism that put glass on your floor? That's what we want to know.
I don't mean to derail, but what about just a small question? What if you're trying to explain why something is faster than something else? Wouldn't that be a question of time, essentially? Why is the cheetah faster than the turtle?
Yeah, but
Physically.
then you would talk about not time. You would say is faster. You're saying this one reached the finish line before the other guy, right?
Isn't that a time issue?
Well, you can say it's a time issue, but you're not going to harp on the time for the explanation. What you're going to say is his muscles are stronger, he runs faster, anything related to biology, perhaps, right? Which is a branch of physics, but you don't need the word time specifically to explain. That's part of the description when you set up your initial scenes, right?
So you're more
The assumptions.
against just using time as an object.
First, using time as an object, which is what the mathematicians do, but that's part of it. The other part is that they've never defined time.
Oh yeah,
That's another one. We're going to talk about that real quickly here. And then the other one is that you have it's part of the description. You can talk about qualitative time without talking about quantitative.
You would say faster. Time. It doesn't have to be by how much.
Or before and after. Later and before. All that is qualitative. It's not quantity. I don't need seconds or years or whatever.
Away.
Okay, so here we go. We have our resident clown, and he raised one issue, and I thought I'd mention it. The rest of what he wrote is poppycock, not important, but let's address something that he raised here, a couple of issues that he raised. He says, here is evidence. I like that. That's a terrible way to start any presentation. Evidence means you're trying to convince someone. So you present evidence. Look, here's the evidence to convince you, to persuade you, to force you to change your mind. That's what evidence is for, and that's what these people are thinking of. They're thinking of evidence, of proof, right? It says, a single atom on the sun emits photons that reach your eyes. A single photon interferes with itself. Single photon, right, little ball, interferes with itself. How it does that, they never explain, they never will. They just say it does. That's their conclusion, that's their explanation, that's their interpretation. But yeah, a single photon, here you see it, okay? Here's the atom, right, creating a wave, travels from a galaxy to our eyes, all the way to our eyes. And the question, does it extend the wave, or does it travel like a little sailboat, right? What is a wave? Where does it start? Where does it begin? Right? This is the question. And so to say that a single photon, we haven't said absolutely anything. Okay, he's got to say a lot more than that. And there's the atom creating the wave. And yeah, so the atom creates a wave, but the question is, how do we get that thing to travel? Does it travel, as a little sailboat, or does it extend all the way from the Andromeda galaxy all the way to us? That's the question, and that's got to be answered, because that's a conceptual issue. We need to understand what the theory is, okay? But then he continues, this is the part I like, he says, the rope model requires a physical, tangible medium connecting every atom pair. Physical, yes. Tangible, no. It's intangible, okay? It's an intangible, invisible mediator, okay? And that's why, the definition of the word object, thing, mediator does not include seeing and touching. You can't see it, you can't touch it. There are objects we cannot see or touch. Straightforward. Air we cannot see or touch. It's made out of atoms. Hopefully air is an object. It's a thing. It's an entity. A medium, right? But you cannot see it, and you can't touch the table that the Klingon has on the other side of the universe. So obviously, see, touch are not the correct criteria. But that's one aspect. Then he says, the 1887 Michelson-Morley experiment demonstrated no detectable physical medium for light propagation. Well, here we have good old Einstein, and he says something different. He says, we have come to regard action at a distance as a process impossible without the intervention of some intermediary medium.
He says it.
He says that. This is Heine. He says this in 1916. He published this in 1920, right? But he's saying you need a physical mediator, otherwise we cannot explain. That's what he's saying.
I mean, that's common sense.
Right. And he continues, he says, if, for instance, a magnet attracts a piece of iron, we cannot be content to regard this as meaning that the magnet acts directly on the iron through the intermediate empty space. But we are constrained to imagine, after the manner of Faraday, right, that the magnet always calls into being something physically real in the space around it. Okay, so there's something in that region around the magnet that we cannot see or touch that is in contact with the iron filings or with whatever it attracts, right? But look what Heine says. He says that's something being what we call a magnetic field. He's going to introduce the word field. thinking that it's a physical object, that it's something that affects something else. And no, a field is a bunch of numbers. It's defined specifically as a value at each point in space. Value, meaning numbers, meaning magnitudes, numbers. Okay, that's what he's talking about. And then he says the effects of gravitation also are regarded in an analogous manner. The Earth produces its surrounding gravitational field, which acts on a stone and produces its motion of fall. So again, he's talking about field. Einstein thinks that a field is a physical object, and so did this fellow here. They all think that the word field can be put in there as a physical object. Say, I'm going to explain to you why this knife falls downwards. And he says, it's the field. You can't say the field, you can't say the energy, you can't say time, because those are just numbers. Those are just concepts that are mathematical concepts. You cannot introduce a mathematical concept in lieu of a physical object.
There's no shape actually touching the knife, is what you're saying.
Right. You need a shape, because that's the definition of the word object. An object is that which has shape, not that which you can see or touch. So this thingy that's there has shape, but we cannot see or touch it. And so the question, you can only imagine it. You cannot go to the lab and try to figure out what it is. Well, you can, maybe it helps you in some kind of experiment, but in the end, you're going to have to just visualize it and say...
Something's touching that knife, though.
Right.
That's essentially what we're saying.
Hopefully this thing doesn't fall... why doesn't it fall upwards? I mean, is something pulling it from above, or what's happening here? No, it's always pulling from the bottom. And yes, it is a pull force, not a push force, as some people believe out there.
Could be pushed, but if it were pushed, they would be assuming that something's touching it to push it, right? But they don't even go that far. They're just saying field, right. It does.
Yeah.
They don't even go as far as to say something pushes it or pulls it. They're just saying it does in this field, whatever that is.
Yeah, and so the question is, you can't use the word field because the field is just a value at each point in space. That's the definition of the word field.
And if that's not what you mean, then
you got to define it differently. Or you have to point to the field and say, that's the field there, and you point to it like you would point to a rock or a tree. Anyways, as bgaede's rope model fails to predict, absolutely, we do not do predictions in science, so we do, predictions are out of the province of science. Okay, we don't do predictions. That's astrology. Anyway, speed of special relativity, by its evidence, is evidence for aberration. I was put a video there about stellar aberration, and he says special relativity is evidence for aberration. So we look up aberration. What is it? Deviation from truth. A departure from sound thinking. And there are synonyms: hallucination, delusions, abnormality. Yeah, that's special relativity. I think we agree there. So yeah, special relativity cannot help us at all. And I'll tell you why. Special relativity is based primarily on this issue called time. And there is no such thing as time. And if there is no such thing as time in physics, that's the end of special relativity. Special relativity is dead, dies a sudden death. Okay, but here let's look at this other word, field, that he introduces there. Here's a field. Doesn't it look beautiful? That's a field.
Looks like water.
And yeah, it kind of looks like that. But what you're staring at, really, and yeah, hold on to your seat. You're staring at number lines. And they're waving the number lines. And that's what they say is the field that makes up space-time. So you're looking at space-time. And what you're really staring at is number lines that are waving. That's what each one of those lines represent. And that's what they did. The mathematicians just introduced number lines, and they put it in this fishnet kind of image. You're looking at a trampoline. You're looking at, maybe a hammock. That's what they're showing you. But what they're really illustrating here is something ridiculous, which is, number lines. And they're putting a physical object there. And so here, this is how they do their physical interpretations. Here you have the black hole forcing a star to orbit around it. And they do it, on the basis of this field. this space-time thing, and what you're staring at is, again, you're looking at the vibration of number lines. So this is not a physical interpretation when they talk about a black hole and a star rolling around it.
I mean, that is a physical interpretation, but it doesn't.
Well, I mean,
it doesn't conduce to any understanding of what we're looking at.
At first, it doesn't conduce to an understanding.
Around a grid.
I could even put angels there, and it would make more sense because you can say, well, the angel's a man with a little plate on his head. He's got a couple wings. Okay, so we're looking at a physical object. Here, we're not even looking at a physical object. We're looking at a field. And what is a field? Space-time, right? The space-time field. Remember, Einstein's is a field theory, right? That's what they call it. And it's just a bunch of descriptions that the underlying substrate are number lines. And they're waving the number lines. And they say, look, there's the physical interpretation for gravity or for whatever. Absolutely not. Okay, so here we have Einstein again. Okay, he says the following. He says, the medium of clocks is influenced by the gravitational fields. Again, we're having fields influencing clocks and time. That's what he's saying, right? And in such a way that a physical definition of time, right, is made directly with the aid of clocks. So he's got all these clocks there. We have a field of clocks, field of time, you could say, right? So their field now has become these numbers, which are seconds, minutes, hours, years, whatever, right? It's a unit of time. And that's what they use as a field. That's the field especially for special relativity. They don't have a field of gravity because special relativity is gravity-less. There's no gravitational field. Right? You don't have gravity in flatland, and special relativity essentially is flatland. You cannot fall downwards in flatland because it's 2D, it's flat, right? But time, they have this field of time even in special relativity. So that's what they're going to use. They're going to use this time thingy. They're going to change it. They're going to vary it. And that's what they're going to say, that you didn't see the same thing that I saw because I saw it first and you saw it second or whatever, right? So they have this issue of simultaneity. What is simultaneous? Is that a word that belongs to time? Okay, is that a category of time, simultaneous? Did you see it at the same time that I did? And here you have Brian Greene, and he's going to cut
the loaf of universe. I like.
Yeah, he's going to take the the Big Bang explosion that's expanding, and that's going to be space-time there. He's going to cut it. He's going to turn it into a loaf. Then he's going to cut it into pieces, and what he's cutting is slices of time. That's what he's illustrating there. Okay. So he's illustrating slices of time.
Why did he choose a loaf as a shape?
Well, it's just showing like you can cut the loaf with a knife. So he's kind of saying he's taking his laser pointer and cutting it in slices of time. The problem with what he's saying is that a slice of time cannot exist. You need two slices to conceptualize time. That's where the whole analogy fails.
Well, to be fair,
you need two slices.
He's essentially using the opposite of what you use when you use the static universe as just as a semantic or a theoretical tool, just to understand, just to go step by step. When you're talking about complicated things, I know you don't like to call them complicated, but when you really go into detail about some of these theories, like since every little word and every little concept can make or break the theory or change what the other person is understanding, you use this static universe tool to kind of explain, okay, let's start off with the static universe before we move it so we're on the same page as that. So in that sense, you could use a loaf of time, just like if you have, because you even use frames of the movie, each one would be a different slice in that sense. But
but each slice of location, he's saying that it's a slice of time. You cannot have one slice of time. You need two slices to conceptualize motion or time. That's where the problem is.
Yeah, okay, that's true. That's true. You can't have one frame of time doesn't make any sense.
Because he's talking about the now, the present. Yeah. The now, the present requires two. If you're talking about time, you're talking about two frames.
Then in a way, he's misinterpreting it when he has a loaf and he cuts through it, because essentially he's using the matter in the universe as the loaf, and he's cutting through it to pinpoint the location of everything in that frame.
Location, yes, but not time or motion. And here you see it. This is what he has. He's got these slices. In one, he shows just one frame of the movie, and
pictures,
the other one,
but those aren't slices of time. Slices of matter.
Time is the whole stack.
Yeah, the whole stack, exactly.
So this is where the problem is. It's misconceived from the start. They're talking about slices of time. There's no such monster. If you put a slice, it's got to be location or distance or some static concept. It cannot be motion or time. Okay, that's where the problem is. And so here he goes. He's gonna fall because of this. He says he can go back in time. Okay, he jumps into a wormhole and he says he can meet himself early in the morning, past, right? So the future meets the past there, and they shake hands. Yeah, sure.
But maybe why? Because he's using the loaf as a physical object. He's saying when he's cutting the loaf of time, he's saying this is an actual thing that I'm cutting. It's not a semantic tool to understand the theory. He's saying this loaf is somewhere in the universe. We are in the loaf.
And this is the issue. Here you have, see what they do. They have this astronaut going back in time, and he's going to meet up with Napoleon. I mean,
okay.
This is the issue. Here we have the astronaut saying hi to Napoleon. He says he can do that with special relativity or general relativity. It doesn't really matter. But relativity in general says that you can go back in time, right, from the present to the past, and shake hands with Napoleon.
I want to see that movie.
Yeah.
Astronaut meets Napoleon.
So this is in the Time Tunnel, they used to have stuff like that where the guy went back in time. I don't know if they did one with
There's
Napoleon.
A lot of time travel movies, but whenever you get even in movie logic, even if you're just talking about like philosophy or theoreticals, it always falls apart eventually. Like if you dig deep enough into the plot of any time travel movie, at some point you'll hit a wall just in your mind. You'll be like, that doesn't make sense. And something will eventually not make sense.
And here, let me show you why it doesn't make sense. Okay, here it goes. This is the Universal movie. This is our tool. Okay, and we all understand what we're seeing there. You take any strip of film that you've got of the old types of film. Now today we have everything on digital. But if you take the old movie films, well, you would see all these frames, and you could see what happens in each frame, right? So we all understand what we're staring at here. The problem is there is no universal movie, okay? So let's make sure...
That's the difference. You say it's just a tool that you use to explain things. They say, no, there actually is a loaf.
Yeah, but let me show you that it ain't. It cannot possibly be, and this is where special relativity and time in general, they both die. Here it is. Okay, so what you really have out there is this. You have only one frame out there. It's always in present mode.
Yeah.
That's what we have. You have every atom in the universe in there, okay? And there's nothing in the previous frame, nothing in the future frame.
This is reality now.
This is reality. It's just a cross-section of time, of motion. It's location. It's the concept that you see on the top. Static concept. You see objects there, you see distance, location, existence, but you do not see time. You do not see motion. Okay? Those are out of the question here. And so the question here is...
Kind of feels like a koan. Like where is time? There's no such thing.
Yeah, and here, this is what we really have, okay? Let's get rid of all the stuff that we have. We only have one frame in the universe, okay? Yeah. And
the movie is always running.
And this is right, and this is what Father Universe really looks like. There he is. One single frame.
Where'd that guy come
from? Yeah, that's Father Universe. Just every atom in the universe. That's all it is. And there is no previous frame and no future frame. If there were, we have a serious problem. That means that every atom is making a clone of itself in the next frame, and then another clone, and that means now I can go back to the previous frame and find those atoms there, because there is the same atom is still there. It's just in a different location. That's not true. The atoms can only be at a different location. They're no longer at the previous location. So you cannot go back in time and land on an atom, because that atom no longer there. Even if we could travel back in time, whatever that means, we would not land on the atom, because the atom is now in the present mode.
It kind of sounds silly that you'd have to explain all this.
Yeah, but this is what the mathematicians play with. They've been playing around with this for since the days of Michelson and Morty ran their experiment, and then you had
when was that?
Well, they ran it in 1887. They ran the last one. They had several experiments. The last one, I think, the important one was 1887. But then you have people who try to explain, because what they were trying to find out is whether the ether existed. Oh. And they say there ain't no ether. There's no proof, evidence, no experimental proof that the ether exists. And people say, oh, no, you can't say that because the ether, we all believe in the ether. And so they came out there, and you had all kinds of people like, Lorentz, and they all believed in the ether, Poincaré, and
they use it to spawn all their virtual particles, right?
Well, we still haven't gotten into the virtual in those days.
Yeah.
What they said, their argument, Fitzgerald and Lorentz and Poincaré, what they argued was that when the reason that Michelson and Morty did not detect any change in the directions in which they sent the light, because they sent the light in perpendicular directions with respect to the motion of the Earth. And they said, look, if there is an ether, it should go slower in one direction, faster in the other. They couldn't find any difference. They say light travels in the same at the same speed in either direction. And so they say, oh no. So they said, look, what's happening in the direction of travel, you're flattening the object. Now they started playing with distance. They said in the direction of motion, what you have is a shortening of rulers. And so they started playing with, the not only time dilation, but they started playing around with the length contraction, and later on with a mass increase. So they started playing around with these variables. But the one we're concerned about is time, because what they did was they left the speed of light fixed at 300,000 kilometers per second. What they started changing was time. Time was a variable, whereas the other one was constant. And so time, they said, for you, time is different than for me. I measure one thing, you measure another thing, and they started playing around that with time in their equations. And here we're saying there is no such thing as time. Not in physics, not in science. In science, there's only a single frame of the universal movie, and whatever happens in that frame, that's it. And here's an example, okay? Here we have two gentlemen, okay, and they have a different distance with respect to an event that happened, which is a supernova. Okay, so there's a supernova, okay? That light is now going to reach their eyes. But what's going to happen here? We're going to have a problem because, see, if you go to the guy on the left, right, he's not going to see the light. The guy on the right is going to see the light first, okay? And there you have the present frame. Neither one saw anything yet, right? But then on the other one, on the last one there, on the one on the right, you see that the guy on the left is going to receive the light much later than the guy on the right, okay? And so the question is, we have a problem with simultaneity, which is related to their locations with respect to the event. And the question is, the only frame that really exists is the one in the center. That's what happened. That's, every atom in the universe was there, not only of their bodies, but also of the supernova. And so what they measure, what they see is irrelevant. That's got nothing to do with what is, what exists. Yeah. Okay? So we have to get rid of the two frames, on either side there. The only one that exists is the one in the center.
This is kind of the reason, or one big reason, why you dispense with the see and touch issue, because of these things.
Yeah.
See and touch gets muddy when you got one person looking at it from here, from there. Well, forget all that. What is actually happening? What does God, for lack of a better term, again, also a semantic tool, what is the all-seeing, like, if you could see where every atom was at every moment, what would that person see? Forget what what us flawed people see, because we can only measure what we can measure.
It's what God sees, to put it in those terms. God has
what actually happened.
Yeah, he knows exactly what happened. Mother Nature knows. Father Universe, they know exactly what happened. We can only measure And again, if the light takes a long time to reach us, we're going to have one measurement and the other guy's going to have another measurement.
But
that's got to do with technology. It's got nothing to do with explaining what actually happened. What actually happened only happened within a single frame of the universal movement.
But that's why we use assumptions so heavily, because we know that our senses or how much we can perceive is flawed. So we dispense with what we see or can touch or all of that. We're like, what can we assume? Yeah. Let's assume this, because then it cuts through any perceivers.
And here, we don't use time in science. We don't use time in physics. Why? Because time does not help us explain. Time is a descriptive concept. It has nothing to do with explaining. Science is about explaining, not about describing. The mathematicians 400 years ago converted science into a descriptive tool, and all they do is describe. They describe mathematically, and they do experiments, to measure and describe more mathematically. That's all they do. But here you have the definition of time. Again, we don't use time in physics, but we're defining it for the mathematicians so they know what they've been doing all these 400 years, because they haven't defined time. And here it is, okay? And time is what? You see it down at the bottom. Comparison of two motions. That's what time is, okay? And so, that's what they've been doing. And what are we comparing? There's an example, the rotation of the Earth around the sun, meaning the orbit of the Earth, right? And a single tick mark on your clock, that's 1 second. And essentially what you're saying is that your tick mark moved your second hand moved 1 tick mark when the Earth traveled 30 kilometers around the sun. That's it. You're comparing two motions. That's all that time is. But again, we have no use for time in physics or in science, because science is about explaining, and time can only help us describe.
At what point in your theoretical development did you kind of realize, because I can already imagine when you started off thinking about all this stuff, you were using time heavily. At some point, you're like, wait, why am I even using time?
For a whole year, I was working on time. In fact, I think I explained that the other day. I was working for several months on this time, and I kept putting it into equations and so on. And I finally ended up, November of, 1997. And in November 1997, I finally started kicking time out of my equation. I said, I don't need time. And finally, in January of 1998, I said, time does not exist. There's no such thing as time. We don't need time at all to explain anything. So it took me several months, but it just held me back because I kept using time because it's in every equation.
Yeah, I mean, we also use it in our day-to-day life as if it's a real thing.
Yeah.
To match up, hey, when do you want to be at such and such place at 2 p.m.? So, it's a useful tool, but it doesn't exist. That's a mind.
Let me tell you something else. What was important, that at least from my point of view, once I got the idea that everything was interconnected, you look at Newton's equation, which is primarily mass divided by distance squared. That distance squared, that distance is not distance traveled. Yeah. It does not involve time. It's separation between two masses. There is no time involved in Newton's equation. There is no time involved. It's a static equation. That's why when Einstein discovered his equation, he says, when we get closer to no motion, we get closer to Newton's equation. Weird. Yeah, no kidding. No kidding, because you eliminate time. Newton, there are two different equations. One has to do with the motion of a point particle around the sun. The other one or a point mass, right, around the sun. The other one has to do with separation between two masses. But then, the more you reduce the motion, the closer you get to Newton. Why? Because Newton's is a static equation. It just says separation between two masses. You already have weight, force, right? Weight. You already have it there. You should be able to illustrate, draw it, right? You should be able to illustrate weight with Newton's equation. And that's what we did. We just said separation, and you have all these interconnections. It's the number of interconnections. Once you get that, you're done. You don't need time, and you don't need to talk about mass. You don't need to talk about anything else. You just say you have two objects separated by distance, and what you have is interconnection between all the atoms. The closer they are, the more the what is it? The interconnections spread apart. They fan out. That's it.